So let's begin the second session of this morning, and we will have a small departure from loop quantum cosmology, and it's a pleasure to introduce Marc, who is going to tell us about...
Hey, I think your mic is not on.
Hello? Hello? Yeah, it's on. It's supposed to be on, right? Yeah, okay. So we're having now Marc from Lyon, who is going to tell us about boundary symmetries in classical and quantum gravity.
Okay, thanks, Alex. And yeah, I'd like to, of course, thank the organizers for the kind invitation to be here. And so I was asked to give a introductory talk for the parallel session on boundary symmetries. So we'll talk about boundary symmetries. So the motivation for thinking about boundary symmetries is, of course, to think at the end of the day about quantum gravity. So here is a list of some questions pertaining to quantum gravity, and I think we probably all agree that these are the type of questions we want to address and understand. So what are the fundamental degrees of freedom of quantum gravity? What is the notion of quantum geometry? What is the origin of black hole entropy? And at the end of this list, what are the symmetries of quantum gravity? So I think beyond the techniques that we use to answer these questions, the reason for which we are together in this room is that we are all interested in asking the same type of questions. And this is a subset of these questions. And of course, loop quantum gravity, as we know, is successful at partially answering some of these questions. We have very beautiful results about amplitudes, description of black hole entropy, microstates, as we heard, very complete framework for talking about cosmology and singularity avoidance. And what is nice is that LQG, this is possible because loop quantum gravity takes very seriously from the onset the classical structure which is given to us by Einstein's general relativity. And in particular, as we know, in these classical foundations of loop quantum gravity, there is a very strong emphasis which is put on the role of symmetries. So of course, background independence, which is the key underlying foundation of loop quantum gravity, diffeomorphism invariance, and also, of course, the local Lorentz symmetry, which is provided to us by the use of the tetrad variables. And this is, at the end of the day, what leads to the fact that we have SU2 spin network states and Lorentz SO31 or SL2C spin foam amplitudes. But if we ask now, if we step back a little bit and ask what are actually the symmetries of general relativity, if it's just diffeomorphism invariance, we realize that asking this question and answering this question is a bit more subtle and rich than it may appear. And essentially this just follows by thinking about, of course, very old results. People have thought about symmetries in general relativity for a long time. This is, of course, based on the use of the Noether theorem. But some of these ideas have come back into fashion in the last 10 years, and I will a bit explain why. And so the question we want to ask is, what does this tell us about LQG, and does LQG have to say anything about this structure of the symmetries in general relativity? So if you ask what are the symmetries of classical and quantum gravity, this is a non-trivial question because, well, already for simple systems, we know, of course, that there are things which I call hidden symmetries. Maybe it's a poor choice of word, but this is just to say that sometimes some systems, even simple systems, can have symmetries which are not very obvious, which are in a sense a bit hidden, and you have to work to kind of exhibit these symmetries. For example, you can, very simple particle model is the conformal particle, which has SL2R symmetry. This is not immediately obvious when you look at this Lagrangian. We know, of course, also in general relativity that sometimes you have geodesic motion. You can have conserved quantities on this geodesic motion. For example, the Carter constant, which is very useful to describe the geodesics in Kerr. And we know that this follows from sometimes some very interesting structure, which is so-called Killing-Stackel tensors or Killing-Yano tensors. And this is, for example, the case of the Carter constant. So this is an example of a symmetry structure, which is a bit, in a sense, hidden in the structure of the theory. You have to dig a bit deep to find this structure. And also, there are, we can talk about symmetries if we describe these very interesting solution generating mechanisms. So the Geiller group, the Ehlers group, Matzner-Missner group, and structures like this. So for us, what will be interesting is to talk about gauge theories. So gravity is, of course, a gauge theory. And there something interesting happens, because when you have boundaries in the theory, well, as we will see, boundaries can support charges and symmetry algebras. And this is a very generic feature. This boundary can be at infinity. It can be scribe plus, for example. It can be the horizon of a black hole. It can be even some fiducial boundary, namely an entangling surface. And in fact, this mechanism is a key to this distinction between what you will call a gauge charge and a physical charge. This is, of course, related to the fact that in gauge theories, and especially in general relativity, there is no factorization of the Hilbert space on a spatial slice, because the gauge invariant observables are non-local, and this is related to the presence of edge modes in the theory. And typically, there is a very interesting structure, because typically what happens is that these boundary symmetry groups, they are infinite dimensional and then contain interesting algebraic structure. For example, this is the case of the BMS group, as we will see in a moment. So given this now, very natural questions arise. The first question is, can we get a handle on these symmetry groups? Can we classify them and understand how they appear? Can we quantize them? Can we represent them? And what does this tell us about classical and quantum gravity? So I referred to Wolfgang's talk on Friday. It will give some insights on quantum gravity from the symmetry point of view. And another natural question is to ask whether gravity is holographic, but I know that this word has a heavy meaning maybe, so maybe a more acceptable term is maybe tomographic. So this is in the sense that Abai talked about in his talk, also Suvrat Raju mentioned this. And you will see that if we try to make sense of tomography or holography for asymptotically flat spacetimes, there is again very interesting structure which appears and which I think is worth trying to understand. So now the final question is, well, if these are features of classical gravity, if we can convince ourselves that gravity has some holographic or tomographic features, then we should ask if somehow LQG should implement or recover some of these features. So to talk about this, I will just have this simple outline with just 3 simple points. And this is just meant to illustrate some kind of interesting aspects of symmetries in 3 different contexts. The first context is very simple. I'll be very brief. This is about mini-superspace models. The second context is in finite subregions, and then I will move to asymptotic boundaries, where I will spend most of the time, and then I will give some perspectives. So, okay, I start with symmetries in mini-superspace models. This will be very brief. It's just to motivate and mention some recent literature. So people who are interested in this can look at these papers, and it's just to mention that even for systems where you think that there is no symmetry structure because these are symmetry-reduced models, there is not much structure, there is still some interesting algebraic structure, and maybe we should think about why this is here and what this can tell us about the physics of these models. So mini-superspace models, as we know, and as we saw in the previous 2 talks, Friedman models, Bianchi models, Kantowski-Sachs models are extensively used in symmetry-reduced descriptions of loop quantum gravity, so loop quantum cosmology models. This is how we have obtained these beautiful results about singularity resolution, so the big bounce, and also these black to white hole scenarios, transitions. And so here I will not focus on the detailed structure of how this is done, but just mention that heuristically we can describe these effective dynamics by thinking about these polymerization schemes. I will refer to this in a moment. And it turns out that in these simple cosmological models, which are in a sense mechanical models, finite dimensional, well, there are examples of hidden symmetries, which can tell you some interesting things about the systems. So this is some work we did with Etera and also Gibril Benachour and the thesis of Francesco. Also Daniele has talked about this on his parallel talk. And for example, to give just an example of how this works, you can take Kantowski-Sachs cosmologies. So this is the line element with the laps, the 2 volumes V1 and V2, which depend on the radial, on the time coordinate. Then this is the reduced Einstein-Hilbert action, which gives this simple 1-dimensional mechanical model. And then if I skip all the details, the statement is that on the phase space of this theory, if you introduce the conjugate momenta pi conjugate to the volumes Vi, you have to introduce some extra quantity. C is the generator of isotropic dilation on the phase space. A is one of the constants of the motion. D is some quantity which you need. Then it turns out that if you consider these 6 quantities here, they have an algebraic structure, namely they span the 3-dimensional, the 2 + 1 Poincaré group. So ISO 2-1. And then using the inverse Noether theorem, you can construct conserved charges on the phase space, and from conserved charges, using the Noether theorem, you can find Noether symmetries of the Lagrangian. These Noether symmetries of the Lagrangian, they are completely non-obvious. If you just start from the Lagrangian, you would never think about acting with a symmetry that generates this 6-dimensional symmetry group. So in this sense, these are hidden symmetries. It's interesting because these are physical symmetries which act non-trivially on the mass of the system. And this is very reminiscent of what happens for asymptotic symmetries. Of course, this is just an analogy. This 2+1 dimensional Poincaré group here has nothing to do with the dimensionality of the space-time. It's just a coincidence in the sense that here it's the 2+1 Poincaré group which comes out. But just for the sake of mathematics and to see what happens, we can, if you have these asymptotic symmetries in mind, we can think about a bit the same thing that happens in asymptotic symmetries, namely the fact that in 2+1 gravity, the Poincaré group is enhanced asymptotically to an infinite dimensional group, which is the 3-dimensional BMS group. Here you can play the same game. You can ask what happens if I allow myself to act not with only these Poincaré symmetries, but with an infinite amount of symmetries on this Lagrangian. These are not symmetries of the theory, but still you get good mileage out of this because you find interesting structure coming out of this construction. So namely by acting with these extended symmetries on the Lagrangian, you can generate some new terms in the theory. You can view this as a flow in theory space. You can generate a cosmological constant, scalar field matter terms. There's also a beautiful rewriting of this simple Kantowski-Sachs action as a geometric action for BMS3, so as a pairing of a Lie algebra element and an element in the coadjuvant representation. And so this is just to show that there is kind of intriguing underlying mathematical structure just for this simple finite dimensional mechanical model. Also, if you have this classical symmetry group, this opens the road to performing quantization just based on the representation of this underlying symmetry group. This was done in a paper by Francesco, for example, in the case of the black holes. And then the natural question, if you have this classical symmetry structure, is to ask, so maybe we can or maybe we should find polymerization schemes which respect this classical structure, because after all, we are just exhibiting a classical symmetry structure in the theory. So if we have a quantization of this model, maybe we should think about whether the polymerization should respect this classical structure. And this is possible, and what is kind of good news is that you can actually find polymerization schemes which lead to these kind of familiar bouncing models. You start with an initial mass, you bounce, and you end up with a white hole with a different mass. And in these polymerization schemes, you actually respect this classical symmetry on the phase space. And the last point I want to make is that this is not just a fluke or a coincidence, because there is lots of work that has followed after this, and you can exhibit this type of symmetries, which are much larger than this Poincaré group, so this Schrödinger symmetry algebra that Francesco mentioned yesterday. And this has a nice mathematical structure because it follows from homothetic killing vectors in field space. And this exists for Bianchi models, Friedman models with scalar field, cosmological constant, Kantowski-Sachs with scalar field, cosmological constant. So it seems to be a very generic feature of these symmetry-reduced mechanical models. Okay, so this was the first message. Then I moved to symmetries of finite regions, finite subregions. So now we are in field theory, and we want to talk about the symmetry content of finite subregions. And essentially, the starting point, what is important, is to go back to the two theorems by Noether. And in the case of gauge theories, these two theorems combine to tell us that to symmetries, we associate codimension 2 objects. So in 4 dimensions, these are surface integrals. And these are the surface charges of the theory. Schematically speaking, these surface charges, you obtain them by combining the symmetry transformation with the symplectic structure of the theory. You also have to go on shell, as denoted by this. The result is a surface term. And very generically, the form of this surface term itself has some structure. Namely, the interesting thing is that it's not only given by the Noether charge which you derive from the Lagrangian, but there are also some non-integrable contributions, hence this delta slash notation, which, for lack of a better name, I call here a flux contribution. So it's this computation of surface charges which allows to distinguish between what is a gauge symmetry and what is a physical symmetry with a non-vanishing charge. There are very beautiful mathematical tools which you can use to actually compute these charges. This is the so-called covariant phase space formalism, in which a central role displayed by this symplectic potential from which you derive the symplectic structure. And I mentioned this here because you may have seen that recently there were many, many papers on this topic, and it seems a bit strange because, of course, this was pioneered a long time ago, and we had results for a long time. But there are lots of subtleties in this these computations. Namely, you have to wonder about the integrability of the charges, about whether the charges are conserved or not. There are cases where the charges are integrable but not conserved, so there are lots of subtleties. Since the charges are not integrable, you have to worry about how you actually define a bracket for these charges. There are many prescriptions for this. In some cases, the charges can diverge, so you have to perform some symplectic renormalizations. You can also argue that there are ambiguities in the definition of the symplectic structure because you can add corner terms. So this is to say that all this recent literature was about how to actually settle down these ambiguities and how, given a theory and given some boundary conditions, you can extract these surface charges. Now the question is whether we can say something a bit generic about these surface charges, because here I might at finite distance, and I would like to argue that at finite distance you can make some fairly generic statements about the structure of these quasi-local symmetry algebras. And the structure that you can exhibit is that essentially there is a quasi-local symmetry group called the corner symmetry group, which is the generic group formed by these quasi-local surface charges, which you can define in general relativity. And very generically, this corner symmetry group has this, always has this form. So it's diffeomorphisms of the two surfaces, some direct product with some group, which I will come back to in a moment, and then two translations. You can think of this decomposition as being, in a sense, kinematical and dynamical, because you can think of this as, you can think of this group as generated by charges. These charges, in a sense, they have two types of components. There are components which stay within this hypersurface sigma. This is the kinematical part. So these are the charges which are kind of integrable from the onset. And then you have what you get when you probe the directions which are orthogonal to this surface. So if you move radially or if you evolve in time. And this is the dynamical component of this subgroup. Asymptotically, this would be, for example, an asymptotic BMS translation or super translation. So you can think about the evolution of a charge as something that kind of stays within a nice algebraic structure, and then some dissipation term due to the flux if you have radiative degrees of freedom. This is a little bit similar. It's just it's not a strict analogy, but it's a bit reminiscent of what Abai mentioned yesterday about split between Coulombic modes, which really live at the corner, and radiative modes, which you see when you evolve in time. And when you take into account radiation, and again, radiation is due to this flux term, is due to the fact that the charges are not integrable. So there is this interesting structure. Now, if we are a bit more precise about the structure of this corner symmetry group, what we realize is that there is a nice way to think about this, which is to inspect the symplectic structure for different formulations of general relativity. And so by different formulations of general relativity, I mean different Lagrangians which describe the same theory on shell, namely general relativity. And if you do that, you can always massage or convince yourself that you can massage the symplectic structure of any formulation F into a bulk piece, which I will call the ADM symplectic structure, and a boundary piece or a corner piece, which is relating the formulation that you're studying to the ADM symplectic structure. And so this kinematical part of the corner symmetry group, which I mentioned here, you can think of it as having this dFs component comes from the bulk ADM symplectic structure, and this group H comes from whatever relative term you have here. So to be more precise, what is the structure? We know you can actually compute examples of this. You can look, for example, at the, so I'm making a distinction here between ADM and Einstein-Hilbert. This distinction comes from the fact that, as we know, the ADM formulation, which, so you could use this Hawking-Hunter Lagrangian, and the Einstein-Hilbert Lagrangian, they differ by a boundary term. This boundary term is the Gibbons-Hawking-York boundary term. But this boundary term carries its own symplectic structure, its own symplectic potential, which you can view as a corner term. And this is why you have this relation here. This is why the ADM symplectic structure is not the same as the Einstein-Hilbert symplectic structure. They differ precisely by this corner term. And because they differ by this corner term, if you compute the quasi-local charges, you don't have the same charge content, and therefore the charge algebra is not the same. In one case, you just have dFs2, and in the other case, you have dFs2 and an SL2R perp, which denotes the boosts in the plane perpendicular to the entangling two sphere. And now for the theory in which we are interested, namely Einstein-Cartan gravity or Einstein-Cartan with the Holz term, you get extra components in this corner symmetry group. Namely, you get tangential SL2R algebra, which will come from the boundary frame. We will get this in a moment. And then you get boosts from the internal Lorentz transformations in Einstein-Cartan and the whole Lorentz group if you use the Holst extension. So now I just want to make a simple argument, which we made in a paper with Daniele and Laurent, and also Wolfgang has a similar construction at null infinity. This argument is to say that just by thinking about this quasi-local symmetry structure, you can argue that, well, area has to be already discretized just from the continuum classical level. And the argument is just to, well, now write explicitly this decomposition of the symplectic structure in the case of what I call LQG here is Einstein-Cartan-Holst, which is the classical starting point for loop quantum gravity. If you do that, well, you will find what we said, that there is the ADM symplectic structure. So this is delta P, delta pi, so the usual ADM symplectic structure on the slice sigma. And then there is a boundary term. This boundary term contains this capital E, which is the usual SU2 flux of LQG. Then N is the internal normal. So it's the normal to the spatial slice, which you have mapped to an internal index with the tetrad. And then there is the contribution here of the Barbero emergency parameter. And then from this frame here, you can compute the tangential metric on the surface S. And actually, you can compute the bracket of this metric from this boundary symplectic structure. And you find that this metric satisfies this SL2R algebra with the emergency parameter appearing here. And now the beautiful thing is that if you compute the Casimir of this SL2R algebra, you find that it's related to the Casimir of the SU2 algebra formed by the fluxes with this important minus sign in front of a square. So this tells you that if you were to build, let's say, states, so for us, spin network states, which are representing the quantization of these boundary symmetry groups, you would, the only natural thing you would want to do is to label the spin network states with representations in the discrete series of SL2R, which leads you to a quantization of the area element. So this is a very quick argument to recover this discreteness of area just from classical symmetry considerations. But now if you are happy that this classical symmetry consideration leads us naturally to an argument which says that the area has to be quantized, then we have to ask about whether we should actually represent the whole quasi-local corner symmetry group, GS, and maybe build spin network states which are based on representations of this whole quasi-local corner symmetry group. Unfortunately, we don't know how to do that, but I think it's an important perspective for the future, because we don't know how to do that because it's a daunting task, because, for example, this is the transition to the last part of the talk, already the asymptotic symmetry group, so the BMS group, whose representation theory has been worked out in 3 dimensions and also in 4 dimensions by Barnish, Ruzziconi, and Lambert. This is only a subgroup of this corner symmetry group. So this corner symmetry group is a very, of course, it's infinite dimensional, and it's a really huge and complicated group, and we don't know its representation theory. Okay, so now I move to symmetries of the asymptotic boundaries, and this is where I will spend most amount of time, because I want to describe some interesting classical symmetry structure, which is, as far as we understand, symmetry structure in classical general relativity, and I think it's quite beautiful. So I move to this. So, okay, so now I want to describe symmetries of asymptotic boundaries, and especially asymptotic boundaries of asymptotically flat spacetimes, so future null infinity. So for this, I take this diagram of Minkowski space in retarded null coordinates. This diagram has the spacetime has 5 boundaries. The boundary which is nicely resolved here is scri plus. I will focus on scri plus, not scri minus, so future null infinity. And this is a very useful picture because, as we know, future null infinity is the ideal place where you can read off the gravitational radiation of the system. And mathematically, this is described by the notion of radiative asymptotically flat spacetimes. So what we want to give a meaning to is how to describe Minkowski plus 1/r perturbations describing gravitational radiation. Why this is interesting? Because this setup here of radiative asymptotically flat spacetimes is the setup in which different topics meet, and these topics are very interesting from the point of view of observations and just mathematical GR and also field theory. The first observation is that, as has been known for a long time, these radiative asymptotically flat spacetimes, they are the setup in which you can talk about, well, I don't want to say new, but not yet observed, but soon to be observed type of observables, non-perturbative observables in classical general relativity, namely the memory effects. So here I have just depicted the displacement memory effect between two test masses who are displaced after the passage of gravitational radiation. And this is the accumulation of this displacement memory signal in a waveform. And so in principle for real physical waveforms, there is a residual strain after the passage of the gravitational wave. This is the asymptotic gravitational displacement memory effect. Now, asymptotically flat spacetimes are also the context in which you can talk about asymptotic symmetries and where you encounter infinite dimensional asymptotic symmetry groups. So this is the surprising feature that far away from sources, in fact, in a sense, general relativity does not reduce to special relativity, because asymptotically, instead of ending up with the Poincaré group of asymptotic symmetries, you have this infinite dimensional extension, which is the BMS group. I'm jumping a bit ahead of myself here for the experts. This is not strictly speaking the historical BMS group, because DFS2 would be just the SO31 Lorentz transformations, but this should be called the generalized BMS group, GBMS, yes. And the last point is that this asymptotically flat context is also the setup in which you can talk about scattering and talk about the S matrix for general relativity or perturbative quantum gravity. And in the context of the S matrix, it has been known since the 60s that there is this very beautiful Weinberg and Low soft graviton or soft photon or soft gluon theorem. This works for any theory of massless particles. And the statement is that this theorem relates scattering amplitudes for n+1 particles, where one of the particles becomes soft, to the scattering amplitude for the n remaining particles, and there is this this factor in front. In this expansion, n equals 1 minus 1 is called the Weinberg soft pole. This is the leading soft graviton theorem. This leading soft graviton theorem at tree level is universal in the case of gravity and in the case of QED, in the sense that it does not depend on the underlying details of the theory. It only depends on the momenta and the helicities of the scattered particles. For n equals 0, in the case of gravity, you get the subleading soft graviton theorem, which is only universal in the case of gravity, but not in the case of QED. And then for n equals 1, you get the subleading soft graviton theorem, which is not universal already in general relativity. It depends on some extra details, hence the dots which are here. Now, in recent years, people have realized that these things, which were known for a long time, actually appear to be connected through nice relationships. And since these are phenomena which take place at long distances or low energies, this is called the infrared triangle. So there is this triangular relationship between memory effects, soft theorems. At the leading order, this is just a Fourier transform between the memory measurement and the soft factors. The relationship between asymptotic symmetries and soft theorems are the ward identities, and the relationship between memory effects and asymptotic symmetries is the fact that you have vacuum transitions. So now to go from here to here is the fact that now there is very strong evidence, yet subtle evidence, that there exist many such subleading triangles in gravity. And the reason for this is that, well, as I wrote this formula for the soft graviton theorem, there is an infinite expansion in this formula. So there is a leading soft graviton theorem, a subleading, a sub-subleading one. So there is an infinite amount of soft theorems here. Presumably there is also an infinite amount of memory effects. This is just a statement that if you set up test particles and you send a gravitational wave through them, they will not only acquire, they will not only be shifted in displacement, they will also, if they have relative initial velocity or acceleration or spin, this can also be influenced by the passage of a gravitational wave. And these are presumably things which you can measure and which are memory effects different from the displacement memory effect. So the question we want to ask is, what is the symmetry interpretation of this subleading structure? If there's infinite amount of subleading structure here, infinite amount of memory effects here, is there enough symmetry to actually support these subleading infrared triangles? So this is what I will try to describe in the remaining 10 minutes. So to describe this, it's very convenient to describe radiative physics at null infinity to work in the Bondi gauge. And in the Bondi gauge, the only thing we have to care about here is that we have this line element. In GUU at order 1 over r, you have the mass aspect. In GUA at order 1 over r, you have the angular momentum aspect. And then this transverse metric here is typically written up to some subtleties with this expansion here. This is the leading component. This CAB is very important. So all these tensors here are transverse traceless. CAB is the shear. DAB has an interesting history of its own. It's related to logarithmic contributions in the solution space and to whether Scri plus is smooth or not, whether or not peeling is satisfied or not. And these remaining terms, this whole expansion is usually called the incoming radiation. So these log terms, I will set them to 0 here. The important point that I want you to remember is that there are 2 types of data here, only 2 types of data. The red data, namely the shear, is data which is completely free on Scri plus. You have to specify the time dependency of the shear everywhere on Scri plus. And then there is infinite amount of blue data, and this blue data is only corner data. It's data which satisfies evolution equations in retarded time on Scri plus, so for which you only need to specify initial conditions at a cut of Scri plus. So this is the corner data, this is the data on all of Scri plus. So the red and the blue data. And this data satisfies infinite amount of flux balance laws. The first of these flux balance laws is the Bondi-Trautmann mass loss, telling us how the mass is evolving due to the emission of gravitational radiation. Yes. What we want to do is understand the subleading structure of the evolution equations for this blue data here. And intuitively, referring back to the triangle that we had before, what one can show is that there is this tower of fields here in this expansion. The first one is the mass, is a spin 0 field. The second one is angular momentum, is spin 1. Then there is EAB, is a spin 2 quantity. The flux balance law for the mass is essentially the leading soft graviton theorem. The flux balance law for the angular momentum is the subleading soft graviton theorem, and so on and so forth. It turns out that to do that, you have to study the Einstein equations at very subleading order, and it's much more convenient to do this in the Newman-Penrose formalism, because this is a daunting task if you want to study these flux balance laws for arbitrary n in the tensorial language. So for this, I just briefly jump to the Newman-Penrose formalism, and the only ingredient we need here to set up the Newman-Penrose formalism is the fact that you need something, of course, very familiar in loop quantum gravity, namely a tetrad. So here, a complex null tetrad. Then from this tetrad, you build the spin coefficients, which encode the geometric properties of the space-time. And then you project the Weyl tensors to trade the 10 components of the Weyl tensor for 5 complex scalar quantities, which are the Weyl scalars. Here I will write the Weyl scalars, but instead of giving them the usual name, psi0, 0, psi1, 0, psi2, 0, I will label this Weyl scalar by their spin or helicity. Because since these are projections of the Weyl tensor on this tetrad, if you project with m and m bar, which are the frames on the sphere, essentially you're trading spin for helicity. So you can think of these scalars as being labeled by helicity. So m has helicity +1 and m bar has helicity -1. So essentially, in terms of the previous data that we had, what is the meaning of these Weyl scalars? Well, the red data is in Q, the charge of spin -2 and the charge of spin -1. This is essentially divergence of the news. This is time derivative of the news. The spin 0, as we expect, is the mass. The spin 1 has the angular momentum. And the spin 2 Q2 has this tensor E1AB. Okay, there is just a subtlety about the choice of tetrad, but now the interesting thing is what happens if you look at these Weyl scalars at subleading order. If you look at this expansion at subleading order, you push this a bit further, you find that there is a very nice structure, namely that at subleading order, all these components are given by this angular Newman-Penrose derivative et bar of a charge of higher spin. So Q -2 at subleading order is et bar minus et bar of the charge of spin -1. Here you have et bar of the charge of spin 0, et bar of the spin 1. So this actually suggests to you that you can, in this expansion for psi 0 now, that you could also introduce higher spin charges in this expansion for psi 0. And you can actually do that by hand. So just do kind of a change of variables if you want. You trade the expansion of psi 0 for higher spin charges which you introduce by putting higher and higher powers of this derivative operator et bar. In terms of the previous Bondi data, these higher spin charges QS are related to this EAB S-1. So this is the expansion of the angular metric in Bondi gauge. Essentially, Q0 and Q1, the spin 0 and spin 1 charges are the leading BMS charges, so essentially mass and angular momentum. Since this is complex Newman-Penrose, in fact, the mass is complex. There is the real mass and an imaginary part called the dual mass. Interestingly, this dual mass is related to phenomenology, namely the gyroscopic memory effect that was described by Blagoje-Oblak and Ali Serraj. And very loosely speaking, you can think of these higher spin charges as being related to the Newman-Penrose charges or the subleading BMS charges. And there's also beautiful work by Compère, Oliveri, and Serraj relating these higher spin charges to the canonical multiple moments of the spacetime. Now, what is very beautiful is that if you now ask what are the Einstein equations in terms of this QS of these higher spin charges, you can show that the entirety of the asymptotic Einstein equations at any order in 1 over n, everything repackages in terms of this compact equation here. So all the infinite amount of Einstein equation becomes equivalent to this infinite amount of recursion relations for these higher spin charges. So for S equals 0 here, this is just the Bondi mass loss. For S equals 1, this is the angular momentum evolution equation. But then you control the evolution equation in Newman-Penrose form for all these higher spin charges, which represents this entire infinite tower of data which is here. Now, to jump ahead of myself, the last thing I want to compute is argue that there is a beautiful algebraic structure which arises from the fact that these higher spin quantities satisfy this compact form of the asymptotic Einstein equations. So to do that, we have to first think about conserved charges, because we want to associate by Noether theorem symmetries to conserved charges. But here, since we are describing radiative spacetimes, this is hopeless, because in radiative spacetimes, there are no conserved charges, because you have radiation. For example, you have mass loss. So the next best thing you can do is to build quasi-conserved charges, namely charges which are conserved in the absence of radiation. So for the mass, it's already the case. The mass itself is conserved if you have no radiation. So for the mass, I can just take my new charge little q0 to be q0. For the angular momentum, I cannot take q1 because q1 is not conserved in the absence of radiation. I have to do this small redefinition using retarded time and this angular derivative. Now this charge little q1 is conserved in the absence of radiation. You can do the same thing for this spin 2 charge, and you can work out a formula which tells you what is the conserved charge up to cubic order in the shear for any of these higher spin charges. Now, the very surprising and beautiful thing is that if you compute the linearized bracket of these charges, so what I want to do now is to rewrite all these charges in terms of the news and the shear. I can do that by iteratively integrating these evolution equations. And then in terms of the news and the shear, I can decompose these conserved charges in terms of a soft part, which is linear in the news, a hard part, which is quadratic in the news and the shear, and then higher order contributions. Then on Scri+, you can use the Ashtecar-Strobel symplectic structure, which is telling you that the news is conjugated to the shear. And using this symplectic structure, you can compute this linearized bracket. Linearized bracket means that I just keep terms which are soft on the right-hand side. If you do this, after a very surprising calculation, you find that this has an algebraic structure, and this algebraic structure is that of what is called the W1 plus infinity loop algebra. And this is the form of this loop algebra. So it gives you an algebra for any higher spin charge of spin S1 with a higher spin charge of spin S2. And so this algebra is actually the algebra which controls this subleading structure of asymptotically flat spacetimes. In fact, this algebra has appeared before in the literature. It has appeared actually in work on twistor theory and also in celestial holography from complicated celestial soft graviton OPEs. So what I have shown here is a rederivation of this algebraic structure just using the more familiar language of the Einstein equations written in Newman-Penrose language. And so this is really the symmetry algebra which seems to govern the subleading structure of gravity. I put self-dual here because in the twistorial proof of this W1 plus infinity algebra, it's manifest that this algebra is only here in the self-dual sector of the theory, or in celestial holography where you neglect half of the helicities of the gravitons. But here for the proof that I have given, I have not needed this condition. So it seems that you can actually promote this algebra to an algebra in all of asymptotically flat spacetimes. And the last point I want to make is that there is also interesting phenomenology associated with these higher spin charges, because if you look at just the soft component of these higher spin charges, you can find that the soft component, there is an explicit formula for this, it's related to higher moments of the news function. And as done by these people, there's a beautiful paper by Grant and Mittman, and also Grant and Nichols, where you can show that the flux balance relations for these higher spin charges, they are related to what they refer to as higher memory effects. So this is really this idea that there is this infinite tower of asymptotic Einstein evolution equations. This tower is related to the infinite tower of subleading soft graviton theorems, and it's also related to this infinite tower of flux balance laws, which if you could measure them, which is probably not the case experimentally, you could reconstruct the moments of the news. So I conclude by giving perspectives, and I just leave this slide here. The point was just to show that there are surprising symmetry structures already in classical general relativity, already in mini superspaces. So the question is whether these are just coincidences or features of general relativity. At finite distance, you can argue that there is this quasi-local corner symmetry group controlling the kinematics of the theory and the dynamics. You have to wonder whether LQG should have states which are labeled by all the representations of this corner symmetry group. At infinity, there is this very intricate structure. And the last point is that maybe this represents new opportunities for loop quantum gravity. And thank you.
Thank you for the talk. We have almost no time, so there is one very urgent question that cannot wait. Okay, so time is up. So,
just a quick remark. I mean, it's not so, it'll be short because it's just a remark. You know, you and everybody else usually say that memory has not been detected yet, but in fact it has. I mean, the statement is that you've got two kinds of observables, ones which are directly measured and the ones which are inferred. Things like the properties of the remnant, the mass and the spin of the remnant in LIGO detectors, that's an inferred observable. And memory is similarly inferred observable. And Neil Khera, Badri Krishnan and I have written a paper analyzing the memory that was actually observed in the LIGO events of the first GWTC catalog, the first catalog, and it's all there, and we sort of see how much memory there is, and we even use this inferred observable to compare various waveform models. So I think that it's not directly observed,
yes,
but
yes.
the final properties of mass and spin are also not directly observed, but it's inferred observable.
Yes. No, thank you. I completely agree. Yeah, I should have made this more precise. Yes.
okay, so let's thank Marc.
And I just had a this was my last.